The audio is working. Cool. So I'm Nick Copi. I'm talking about following the JSON path, a road paved in RCE. So first of all, who am I? So I'm an AppSec engineer at CarMax. Great team, great security team we have there. I think we have a couple openings on the compliance and risk side. If you want to go by our table and check it out, if you're interested or know anybody that might be interested. So I do that by day, and then by night I do independent security research, bug bounty, falling down interesting rabbit holes into interesting applications. So I'm VCU alumni, did a CS undergrad degree there, former cybersecurity club president there. Great time, great experience, great people. I'm the RVAsec CTF reigning champion, so I'll be doing the CTF again tomorrow, and you can come put me in my place and dethrone me. I'm a ThinkPad dual wielder, as pictured here, and you've got a rare instance where you've got hackers and salad in the same photo. So I don't know if you'll ever see one of those again. I've got my website up there, and then just the fun fact is that I've probably spent more hours debugging JavaScript in the last year than in direct sunlight. It's something I'm working on. I think maybe I'll get some sunlight this summer. I'll definitely get more JavaScript debugging in. Good point. All right, so about the topic of the talk. So the title is a little strange, Following the JSON Path, a Road Paved in RCE. What is a JSON path is kind of the first question. And so if you're familiar with XPaths, which are a way to refer to a selection of XML elements, it's like that, but for XML. If you're not familiar with XPaths, you've got an input JSON object. It doesn't matter what it says. You can't really see the text here, but it's big. And you've got a JSON path that selects some content out of it. So it gets .context.address, and then it's got this little thing here, and this is where the magic is. So this is a filter expression. So it selects all of the items here that have a type of billing address. And so we see here, this is what the output for that would be. But the question is, how do these work? So to set some context for this, in August of 2024, I'm doing some undisclosed bug bounty research on a Target application as part of a public program on HackerOne. I know they are running an Express.js API, several of them. There's a lot of ways to fingerprint that. It handles certain objects certain ways. But anyway, I come upon some API endpoint that receives an input JSON object and then a JSON path and returns the result of querying the input with the JSON path. So the question is, how is JSON path parsing implemented, and how are these filter expressions implemented? Because if you look at this, this kind of looks like JavaScript. So it's kind of like looking at this, I saw this, and I got really excited because I'm like, can I just put arbitrary JavaScript here, and it'll run it server-side, and then I can pop a shell? The answer is not quite, but we'll get there. Any time that you're running user-provided code in a secure context, it's no good. So we also need to talk about what an abstract syntax tree is. So if you have like a traditional CS or developer or whatever background, you're probably familiar with this. But essentially, it is a tree representation of the syntactic structure of source code or expressions. So in the context of JSON paths, these filter expressions, insane implementations, get parsed out into an abstract syntax tree that's used to implement the evaluator for them so that it can select out the matching items. And why this matters for hacking is because this is essentially what's getting executed when we provide that user-provided JSON path to the remote server. And so it's using an AST evaluator, as we'll see. And unfortunately, these can be implemented in ways that cause breakouts via accessing global objects or prototype chains, which we'll get into in JavaScript, or just arbitrary code execution. So that's worth playing for because getting server-side execution on this API that we're looking at is definitely valuable. So I want to break this. I want to figure out how those JSON paths are getting processed and how it's filtering out the objects. So I just Googled JSON path NPM. And this is the first thing that comes up, 2.7 million weekly downloads, but it hasn't been touched for years. So I decide, all right, I'm going to get hacking on this. So what do you even do to get that tested? So I set up a local lab. So I've got a Docker file that runs with the node debugger, and then I've got just a very simple web server that defines one route that takes an input object and then a JSON path, and then passes it to the JSON path library and sends back the response. So now I can connect my Chrome DevTools debugger to this instance and then debug the implementation of the JSON path library and figure out how is this processing these paths and can I get arbitrary JavaScript execution. So what this lab does, we can post to it an object and a filter, or a JSON path with a filter expression, and it gets the results of evaluating it against it. So it selects out these items because that's what that filter matches. So looking into how they implement filter expressions, so script expressions and filter expressions. So script expressions are less available, filter expressions are more available. We're going to be focusing on filter expressions, but they use the same backing eval logic. So they're statically evaluated via static eval, which this is dchester JSON path saying this, and they're saying that this is safer than using VM run in new context, since the script engine itself is more limited, blah, blah, blah. When you look at static eval, which is another NPM dependency, it says, do not run this with untrusted code. So this is a really good sign for us because we've got the library maintainer for the JSON path library suggesting this is safe. You can run untrusted user code this way. And then the library that they're using to run the untrusted user code says, don't do that, please. Very good sign. I got very excited when I saw that. Unfortunately, it was a little bit more complicated than that. So static eval builds and evaluates a very limited functionality abstract syntax tree of our expressions we hand it. So there's a lot of things it supports and a lot of things it doesn't support. So like assignment of like data to variables is not something it supports because it's static eval, so it doesn't support any assignment operations, and there's just a ton of like newer JavaScript features it doesn't support. But the thing that it does have is several protections to try to prevent arbitrary code execution, but they're not bulletproof. So to get into how we even get arbitrary JavaScript execution from these paths, we don't have references to powerful things like eval or bigf function. So bigf function is like eval in JavaScript. It's called the function constructor, and you hand it a string, and you call it, and it returns a function that evals that string. So this is pretty powerful. It's an interesting sync if you're just analyzing source code and you see they're calling bigf function with user-controlled input. That would be bad. In our case, what we're interested in is getting a reference to bigf function without having bigf function in scope. And the way that we can do this is via JavaScript inheritance and constructors. So essentially, the way that JavaScript works is there's a prototype chain. So for example, when you just have a string object .substring is equal to big string constructor.prototype.substring. And so there's this really silly inheritance that allows you to go from just like a primitive object to some pretty interesting stuff. And in that AST evaluator, we only really have JavaScript primitives like strings, arrays, objects. So if we can work our way from one of those primitives like this to the bigf function constructor, we can then pass it a string with arbitrary code and then call that, and it'll essentially eval it outside of the context of the AST, and we're golden. So fortunately for us, those constructors are available via .constructor in JavaScript. So if we have any function in JavaScript, if we call .constructor on it, we get a reference to bigf function. So string.substring is a method from string's prototype, and .constructor of it is bigf function. So we can do something like this, and this actually leads to code eval. So despite the fact that we don't have bigf function in the AST evaluator, just from a string primitive, or literally any function, we can call .constructor on it, get bigf function, pass it a string we want to execute, call it, and call the result, and we have eval. Unfortunately, static eval does not want to let us do this. So debugging it, I'm skipping a lot of other checks that aren't really relevant for this. This is kind of the mortal enemy. So I'll break this down a bit. But essentially, the member expression AST evaluation step, which is like calling dot constructor. So when we're calling dot constructor, that's a member expression. It's getting a member of an object. It will not return functions, or it will not return things where type of obj equals function. So when we call dot constructor to try to get a reference to it here, or dot substring to try to get a reference so that we can call dot constructor on that, it'll actually just fail because we're not allowed to have references to functions to try to prevent this kind of scenario. However, this is where things get really interesting because all this is doing is checking that type of obj is equal to function. We can work around this via JavaScript prototypes. So every object hold for ones created with object.createNull have a prototype implicit value. So it's type-based. So for example, just on an object, proto is an object, and its constructor is the object constructor. We can play some tricks here, though, where we define an object and set proto. So here we're creating an object with a prototype that is the function. So value of is a built-in function that exists on proto, and so it can be resolved from any object. And so our prototype, instead of being an object, is a function. So when we check dot constructor of this object, despite the fact it is an object, it's not equal to object. That's false. Instead, it's equal to big F function. So this is very interesting because that's what we want to reference to, but we're not allowed to get member expressions that return functions. However, in object definitions, that's fine. So we can define proto to be a function, and then dot constructor will be big F function. And this leads to a scenario where we've got this object right here, where when we run type of, it's object, but when we get dot constructor, it is the big F function constructor. So despite this check here trying to prevent a scenario where something with a function constructor is returned and then callable, we can work around it. And so if we take this object, get constructor, which is big F function, pass it a string, and then call that function, we get code evaluation. So we can actually put this together into a full RCE payload for JSON path. So we build out this input object. It's just running a filter expression on each member of it, so that's what that dot dot is. And so it's only got one member, so this only runs once. Then it uses that trick object where its constructor is big F function, but its type of object, which in the eyes of static eval shouldn't be possible just due to their naive checks. And then this imports child process and just calls ID, and we get just code execution. So we've got that working in our local lab, which is great. But it turns out I hacked the wrong thing. So it turned out that I threw the payload at the target quite a bit. It had some strange character restrictions, so I had to warp it and adapt it a lot, and it just wasn't popping. And so I look into this more, and I'm like, oh, there's actually another major, even more popular JSON path library for JavaScript. So I guess we got to pop that one, because all that work was for nothing, apparently. So I set up a lab. It's basically the same code, but we swap out JSON path for JSON path plus. And it's the same Docker file, so we can attach our Chrome DevTools debugger and start tearing it apart. So just reviewing the code of this implementation, it's a lot more straightforward how it does evaluation. So effectively, what it ultimately does is it uses VM from Node.js for execution, and it uses vm.script.run in new context. So this is some functionality that's built into Node.js. It is not safe for sandboxing. It is well known and well intended that you can get arbitrary code execution that exits this arbitrary context that it's running inside and just runs in the main node process, just calling some object.constructor.constructor, getting a big F function reference. There's nothing to try to stop it because it's not supposed to be secure or safe. And it should be trivial then for us to shell our target. So when I was digging into this, I was not under the impression that this was a vulnerability in JSON Path Plus, but a deliberate design decision. So this prevents any scope overlap that the filter expressions run in because they're given this context, so nothing global is exposed to them. And there's also an option for JSON Path Plus called eval false, which disables these entirely. So it seemed to me that this was a mistake of the developers of the application I was targeting, where they should not be calling JSON Path Plus with a user-provided or user-constructed JSON path without running JSON Path Plus with eval false to prevent this exact scenario. So I was able to get just a blind RCE payload put together. So this worked against the local test instance. It's just, again, using the fact that these big F function constructor called evaled expressions have a reference to process, which in Node.js, this is like a global variable that has a lot of information about the current running node process. In older versions, it has .main module .require, and what require does is it lets you import native node libraries. So child process is one that gives you like spawn and exec file and exec sync, and that lets you run binaries on the disk. And so we can just pass a command to it and call ID. So ultimately, for the target, I did have to end up modifying, putting together quite the extensive payload. So I had a character limit. They had a ton of character restrictions. Fortunately, though, because we have effectively JavaScript execution, we can encode stuff pretty hard, and it'll get decoded, and we can work around those character limits. I actually ended up building a stage 1 script that reached out to my remote server, grabbed some JavaScript, and then executed that. And so I was able to get a reverse shell back from it, reported it to them, and they paid out. But the thing is, okay, that's nice and all, but like, where are we now? So I found the bug in the first one. I found that the second one is pretty easy to misuse in such a way that leads to code execution. What else is impacted by this? Who else is misusing these? Who's using the older library? So dchester JSON path, it's hopelessly unmaintained. It's had a prototype pollution issue open for the last 4 years, which is another type of security vulnerability that can, in some cases, lead to code execution. But the maintainer hasn't touched it, despite everything being used. There's no disclosed vulnerabilities here. Don't use it, it's bad. Use this one. This one is also claimed to be unmaintained. The author said as of February 2024 that he's not maintaining it any longer. And this can be run with eval false and be totally safe. And it didn't even seem like a security bug at the time. I did find out later, and we'll get into that it was. Spoilers. But yeah, so the question is, who all is downstream of these? And do they use the library in such a way that JavaScript execution can be achieved? So JavaScript execution in a server-side Node.js context, remote code execution, you can import child process and just run arbitrary commands. In a web-packed browser context, you get XSS. So depending on where they're using this, there may be different impact. Definitely a lot more interested in the scenarios that lead to code execution, but I'll take some XSS bugs too. So digging into dependence of these two packages, who uses these, who consumes these in the open source space? Because we can't really see closed source usage of these. You know, we see that there's like 2.7 million downloads a week for one of them, 5 million for the other. We don't really have great visibility into who's pulling those. The only thing we do have visibility into that we can realistically look at is open source dependence of these two packages. So the idea was, okay, there are solutions that aggregate this data. They pull it and aggregate for us and make it searchable. So I created a libraries.io account, registered, got an API key, and it turned out they had disabled their dependence API for performance reasons. That made me unhappy. I still haven't forgiven them. Maybe one day I will. But this would have saved a lot of time and made things a lot easier. So instead, I just said, you know what, I'm going to scrape it. I don't know, can I list this from an API? So NPM has pages that list the packages depending on for an arbitrary package. I just decided I'm just going to write a scraper because I want them sorted by number of downloads, and then I want to look through the ones with the most downloads and figure out if they're impacted. So I just wrote an awful scraper. I used this for both JSON, or Dchester JSON path and JSON path plus. I ran it, and I got output here, and so now I can sort by NPM dependency names and the number of downloads. And so this gives me a great space to start looking into these. And so the big thing I'm looking for is stuff that might be, well, number one, impactful and should probably be fixed. And number two, stuff that is covered by bounty programs of companies. So if I can find stuff that is impacted by this, I may be able to get a bug bounty payout for it, which is an interesting way of going about discovery of that kind of thing. But yeah, I also wanted GitHub dependence, which tragically, again, did not offer a way to sort by stars. So GitHub actually does tons of SCA stuff. They do a dependency graph, but they also do dependence of packages. And so they actually track all this, and it makes sense because I guess Microsoft acquired both NPM and GitHub. It's kind of funny that they have the data separately and that I had to scrape both. There was no way to sort by stars. If I could have done that, it would have saved on about a week of scraping. But I wrote an awful scraper again, and it was just a whole lot of this, and a lot of timeouts, and a lot of bad parsing and restarts. But I just wanted the first couple hundred sorted by stars, and so I had to get all the several million of them. And then ultimately, I got about 51 megs of data for the larger of the two sets. And I was able to sort by stars for usage. So analyzing this data. So there's a lot to dig into here. So there were a lot of cases where the dependencies are used with fixed JSON paths. So there's not any way to inject arbitrary content into the JSON path and say, add a malicious expression that leads to attacker-controlled JavaScript execution. And there were a lot of cases where the JSON paths the JSON path reference was a transitive dependency of something that used it safely. For JSON path plus, I actually saw a lot of users running it with eval false, which was good because if they were handling potentially untrusted JSON paths, that was the correct way to do it. I did see a couple of targets that kind of disappointed me with that because I think they would have paid out if they hadn't been running it that way. But skipping through all the dead ends, let's get into some scenarios with impact. So this was probably my favorite one just because the team was pleasurable to work with. But these little badges that people like to throw in their readmes on GitHub repos. So these are, for the most part, the most common service for generating and hosting these is Shields.io. So they have an open source version of their code base that generates these badge images. And it was something that was found in my exploration. And notably, with these GitHub dependents, there was a ton of hallucination. I don't know what happened, but there were so many cases where I would look at an app and it would not even reference the dependency. And it would be like a Java app with no JavaScript at all or something. I don't know what's going on GitHub's end there, but fortunately, this was not one of those hallucinations, and I was actually able to go in and dig deeper into this. So it has an endpoint that grabs JSON from a URL and a JSON path query and passes it to Dchester JSON path. Well, fortunately, we have put together already a payload that, if used to filter in a JSON path, executes an expression that leads to RCE. So essentially, you could hit the badge dynamic JSON endpoint. You give it some URL that points to some JSON object. I don't know how it downloads these. I don't know how it's safe. There might be SSRF here. This just seems like good SSRF attack surface. I've not looked into it. That's some free research anybody can follow up on if they want. It also takes a JSON path query. So we can hand it our dchester JSON path payload that tricks the AST evaluator into letting us get a big F function constructor and execute an arbitrary string outside of the AST, and then call child process sync and run whoami. So I had a local lab set up for this as well. I really like that model of running Docker containers and then running node and binding and exposing the debug port and just kind of attaching to it. It really lets you get deep and dirty with all that's going on and lets you see everything. So I reported this to their security contact address with a full POC against my local instance of the open source version. So I never actually threw this at their SaaS server. I'm sure it would have impacted it because I'm sure they were running the same code, especially based on the fact that they fixed it in 3 days. They were very professional, and it was the best experience I've had with open source vulnerability disclosures. And we got CVE 2024-47180 assigned. So yeah, it's funny to think about what could have been done with this. If you'd popped the Shields.io server and made it serve arbitrary content in people's badges, that would have been bad, I guess. But yeah, so that was great, and they fixed it, and they actually identified a couple other endpoints that took similar parameters, and they moved over to JSON Path Plus, running it with eval false. So that was actually part of the reason it was such a great experience, because a lot of these that I reported had partial fixes that weren't great and could be bypassed. And so we'll get into some aspects of that a bit more, but these guys got the job done and fixed it. RCE and Mountebank. So this is a mock testing server. So essentially the concept with Mountebank is I'm a developer, I have integration tests that require talking to some API. I don't want to talk to a real API because this is just stuff running at test time. I don't want to modify real data. What Mountebank does is allows you to define stubbed out API endpoints as code, and then those can be used at test time. And so this is like a dedicated instance that runs persistently. You define the stubs that create listeners, and the app at test time talks to those stubs, and the integration tests run properly. The problem is they used JSON Path Plus without eval false, and when you create a stub listener, there's support for a selector that's a JSON path for like defining the stub and what it should return. And we can inject our JSON Path Plus payload that just calls big F constructor, getting it from dot constructor, which is, this is the object constructor, and then this is the function constructor because we're calling it on a function. And running our arbitrary code. So I got a local lab with this setup, and essentially you make 2 requests. One of them creates the stub listener, which by default, Mountebank runs unauthenticated. Anybody can just call to it, that's really its own problem, but it shouldn't lead to RCE, but it does. And so then you hit that stub, and it processes that JSON path with some data, and you get code execution. So I emailed the security email, but apparently the project is abandoned, which is not great, because I heard earlier in 2024 about new cases of people spinning this up, so it's unfortunate. And then as of May, I guess as of June now, I haven't heard anything back from them, and I do not think this is getting fixed. So this is a stub here. So I got RCE in an undisclosed Fang application. It was using dchester JSON path in a way that allowed for remote code execution. It was exposed only in a niche scenario. So the application itself ran at CI time in theory, and it ran in such a way, and the source that led to the JSON path sync was kind of weird in such a way that it was kind of like unlikely that someone would run it in such a way that it would possibly pull untrusted data. It got accepted to be fixed, but the VRP panel decided not to accept to pay out a bounty for it. I was hoping it would be disclosed, but it was not. And so I can't really say what it was or who it was, but there is certain language that's used here that if you know what some of these words are and some of the language used by some of these companies, it says who it is, which is funny. Another one, and this one I can say even less about, XSS in an undisclosed FANG application. So it was an open source application that used JSON path plus / JSON path in such a way that allowed for stored XSS. So it was like a multi-user account system, and so like a lower privilege user could create certain configurations that would lead to the processing of a JSON path provided by that user in the browser context of anybody that viewed that page. And so because you can provide an arbitrary JSON path to JSON path plus running without eval false, you can get JavaScript execution, and so anybody that loaded that, it would execute whatever JavaScript was thrown in there that broke out of the intended or lack of intended preventions and just get XSS effectively, because it's in a web context. So I was able to use that to show account takeover via session hijacking. So it would steal the session token. I think on this one there was like some token refresh endpoint that it could just fetch to in the JavaScript payload and then send that to a remote attacker server. And then bug bounty was paid out. It wasn't hush money. It was bug bounty. There's a difference. So this one's not disclosed, and I can't really say who it was or what it was, but it was an interesting scenario. DOM XSS and CyberChef. So this one is sad because it's still not fixed. But CyberChef, if you're not familiar with it, it's a tool for transforming input content to get an output using recipes defined by a user. So it'll do stuff like base64 decoding, hex decoding, various like decompressions. It's got a lot of interesting obscure things. It's generally used in like CTFs when there's a bunch of challenges that are just like, that involve encoded texts with layers. It's a nice visual tool, but it also supports JSON path lookups client-side using one of the JavaScript libraries, JSON path plus, and we popped that. So let's see if we can impact CyberChef and get XSS. Specifically, the reason I was looking at this was because I was looking at an appliance that shipped with CyberChef. So it was like a web application. You could log into it with users and do stuff. And it just had a /CyberChef page because the stuff you did involved network traffic. And so maybe you'd want to decode some stuff and have CyberChef handy. And so it shipped CyberChef built in. So if we could get XSS and CyberChef in that context, we have XSS on that appliance, and then we can actually use that for nefarious stuff like account takeover via session hijacking. So CyberChef, here's kind of what it looks like. It supports JSON paths. So we have our input example object here. We have a query. So same thing where it's just doing value mod 3 is 0, and then we get the items that are matching that expression. So this is happy path, JSON path working, nothing nefarious happening, intended usage. So the question is, can we just throw some variation of our payload that leads to arbitrary eval of JavaScript at it and get XSS? The answer is yes, sort of. So here we see it's processing this JSON path. We see in the JavaScript console that console log leet is running. So it looks good. Unfortunately, we actually only have execution in a web worker. So a web worker in JavaScript, it's a client-side browser concept. It's analogous in some ways to a thread. It's easy to think about it that way. It's non-blocking to the main rendering thread. So if you're doing things like, computing complicated stuff here, these might be some real long recipes. It runs all of those in a web worker. so that it doesn't block the UI and the UI doesn't like freeze and lag when it's trying to calculate all that. But it does not have access to DOM or browser APIs. So that means we can't do things like access local storage, we can't access cookies, we can't access anything in the DOM itself, so none of the elements on it. We can't even call an alert. And so if we have an XSS and we can't even pop an alert, that's really disappointing. And the way that it talks to the DOM is via post message and on message. So essentially, event handlers are registered in both the worker and the main thread, and it's able to send bidirectional, effectively just JSON encoded messages between them. And clearly there is communication between these, because when this JSON path is evaluated, it needs to send the response back to the DOM so it can render it. So what we want to do is break out of this worker context and get into the main renderer by abusing the message channel to, okay, well, we have JavaScript execution in this web worker. We're going to then talk over this channel to the main thread and tell it something that leads to migrating the XSS to the main thread. So I spent a couple hours reading through the relevant code in the CyberChef repo that's used to create these web workers and evaluate their recipes. All the language it used was so silly. It's all very like cooking themed, and it's about baking and all kinds of stuff. But what I found was a code path that would lead to being able to send a source, so attacker-controlled data, over that post message bridge that the web worker uses to lead to an inner HTML settings sync. So this sync runs in the main process and takes data provided from the web worker and passes it to .innerHTML, which allows us to get XSS then in the main window in theory. So certain recipe types actually support HTML outputs. So for example, this right here is a recipe. It's a JPath expression is what it's called. In the case of those, that content type is not HTML, it's application JSON. However, the message type for sending a completed bake back, it uses the type of the step. So even if we told it, yeah, this is HTML, it would actually ignore that on our message and say, no, this is for index 0, which is a JSON path evaluation. That returns JSON. I'm not going to render this HTML. However, what we can do is add a step that uses an HTML output. So certain types allow for HTML output and are intended to render HTML. And we can send a bogus message that uses that input. So it's evaluating the JSON path expression, and then we send a message back that says, hey, I just completed a bake for this other guy. Here's the HTML to render. So the extract files step takes HTML output. So we can pass it an iframe with a JavaScript URI source. So this is a great way to get XSS via setting.innerHTML, because if you just pass it a script tag, those don't actually execute via .innerHTML. But the crucial thing we're doing here is lying about the input number. So we say, yep, this was for item number 1, which is, because it's 0 indexed, it's the second item. And then it will render that output as HTML, which lets us pop our XSS. And the coolest part about all of this, and the reason that this was all worth doing, is these settings for all of this are actually stored in the URL. So it sets the recipe there. And so you can just create a link. So if you navigated to this right now, it would pop the alert. I have it up on my blog. If you remembered from the beginning my website, you can find a link to my blog there, and there's a whole write-up on this specific bug. And it is unpatched. So I emailed them back in December. I think I saw several other reports of similar bugs, and they just don't seem to care about fixing XSS and CyberChef, which is really unfortunate. I've seen cases where there have been fixes for bugs, but the problem is that you've got these third parties that ship with CyberChef. So yeah, like I mentioned, I was able to then get this weaponized, so I migrated the XSS from the web worker to the DOM, able to implement an attack scenario where I was able to steal session tokens for this third-party open source application that shipped with it. I reported it to them. They responded. It did not seem to be a huge priority to them. So it's just unfortunate. And there's a whole can of worms that can be opened here that one could do a full talk on. There's just a lot of cases with these nebulous vulnerabilities that aren't tracked well or dealt with in open source that actually have a lot of impact. So some honorable mentions. So I found like a random low UI DOS bug in Rancher dashboard. I looked at a couple Postman alternatives. If you're familiar with Postman, it's like an API client. You can build specs and stuff. A lot of them offer JSON path parsing. Some other undisclosed XSS bugs, as well as some unknown unknowns. I'm sure I'll continue to find things in the closed source space that use these. Things got interesting though. So come October 2024, a critical CVE for JSON Path Plus dropped. And so I didn't know what was going on there. At first I thought it was one of the Feign companies that I'd reported things to had decided that I'm gonna go bully the dev that owns this and get them to fix this and decide that it's supposed to be safe. So it turns out that evaluating arbitrary user-provided JSON paths with the default configuration was supposed to be safe. It was not supposed to be totally insecure, so it was not the developer's fault. It was JSON Path Plus's fault. But the question was, who else was looking at this? And so this was the CVE that went up, and I saw this, and I'm like, wow, I could have had that CVE. That would have rocked. In my mind, it worked better that this was a footgun, because then I can go to the developers using it wrong and be like, this is a bug in your code, you need to fix your code, and then in the case of bug bounty, I get paid for it. So I ultimately, enough information dropped that I was able to reach out to the guy that reported this. And so it turned out it was an Italian cybersecurity student and a highly skilled CTF player. So I'd thought it was probably one of the Feign companies, but he had noticed that Insomnia, which is one of those API clients, used JSON paths in some interesting places. So to quote him, at some point he'd made a mistake while writing the filter on some object properties, and he wrote an equals instead of an equals equals, and all the objects had the properties replaced, and he didn't think that was right, so he dug into it and ended up getting RCE. So he was able to report it through Sneak, so they sponsored the conference, and they offer vulnerability disclosure. And they actually do a great job wrangling the developer for you. So a lot of the times when you're reporting to these open source developers, maybe they don't respond, maybe they don't care, maybe they don't understand the risk, maybe they're done with maintaining the project. I don't know who Sneak has wrangling these guys, but they seem to get things done, so that's impressive. But after some blast radius exploration of his own and some reports to fix stuff I'd either missed or didn't feel like dealing with, he was pretty happy with his exploration of it. He had a lot of back and forth between him and the developer, bypassing fix after fix, and I had a great discussion with him, and it was very interesting insight into someone else looking at a very similar problem, and it was cool, just like the strange networking and how interconnected everything is, where it's like, yeah, I don't know, I guess I can find myself talking to an Italian CTF player about a CVE that could have been mine. So JSON Path Plus, it kind of entered a dark age. There were a bunch of bypasses done. Long issue that was, this is just the more, so this was a public issue on it, and just bypass after bypass fixing, or of that fix, and eventually it stabilized. So by January 2025, the dust had settled, and I decided that I would look at it myself. They had moved over to an AST generator / evaluator. And so we want to do the same thing here. We want to call big F function, and we want to get arbitrary JavaScript execution out of the AST evaluator. So the big thing they did is they added this list of blocked proto properties that you're not allowed to get. Fortunately, it was not implemented properly, and we'll get into that. But these were intended to prevent bad things from happening by processing these expressions in their AST evaluator. So they have a check here when you are getting a member expression, so similar to the other library. But they check the object has own, that property. They check that it's not in the set of blocked properties. And if it is in the set of blocked properties, or the object doesn't have the property, it'll throw an error and not read it. Otherwise, it'll index obj with prop and set that to the result that gets returned. So some very interesting behavior here. Here's a similar implementation that kind of explains the problem. So here's our set, here's our object, here's our prop. We check if that set has that prop. In our case, our prop is an array that contains the string constructor. So our set does not contain that because our set does not contain any arrays. It contains 2 strings. So this does not get tripped. Then when we index into obj with prop, toString is implicitly applied on prop. So because this isn't a string, toString is applied on it, which returns just constructor. So in JavaScript, when the implicit toString handler for arrays, it takes the string representation of each object in the array and puts a comma between them. Well, there's only one item, so there's no commas added, and it just returns the string constructor, which was supposed to be blocked, but because when it was checked, it was an array, but then when it actually resolves it, it converts it to a string, we can just bypass the check, which lets us put together a real clever payload like this. So we index that constructor wrapped in an array twice, get the true function constructor, and can call arbitrary code. So CVE assignment, I got a CVE for it after all. So loot and accolades. So 2 critical bounty payouts, 1 high bounty payout, 1 medium bounty payout, about leet with an extra E total, and then at least a couple critical CVEs. So these 2 things are unrelated. This was the JSON, no, this was the images shields CV or GHS AID, and then this was the undisclosed original program that I got pulled into this to begin with, and they were able to pay out a nice bounty as well. So lessons learned, no standard for JSON paths until early 2024. Very interesting because the implementations definitely showed that there was no standard. There's no such thing as safe JavaScript execution, except for when there is, but even then there isn't. And then don't treat libraries as out of scope when hacking an application. So by default, like when you attach Chrome DevTools to a Node app, all of the Node module stuff is like hidden from debugger, and you have to like right-click enable. There's a lot of opportunities for strange footguns and just interesting gadgets and ways that these libraries behaved when passed data that the developer doesn't intend. Then also just be friendly with other researchers. I think it was a really great experience to get to talk to the very skilled Italian CTF player that stole my CVE, and at the end of the day, I was still able to get another one by bypassing the fixes. So questions? I think we're dangerously close on time. Chandas.
So when's the CTF competition between you 2 going to see who's better?
I'm sure he's a better CTF player. He's a CTF player that does like online CTFs. I think he's in a very good team, and I'm sure he would absolutely destroy me.
Yes, bumper skills.
Austin.
Hey, when it comes to vulnerable abandoned libraries, where does the disclosure fall? Is that on the developer?
Great question.
Vulnerable management teams?
So the reality for that is I should probably throw a report into Sneak through their disclosure and try to make them deal with it. You can actually try to file a CVE yourself. There's other research out there. I actually found a Korean researcher that had dived into some of this in 2020. I was able to find web archives and machine translations after I'd popped it. So some of this is like semi-known, but it wasn't taken to the extremes and the paths weren't all followed out. But there's a big gap there, and somebody could probably honestly do a whole talk on that subject alone. All right, I guess Austin again.
One more here.
Yeah.
Since CyberChef doesn't plan on doing any patching, do you plan on focusing on that a little bit deeper now? Or?
It's hard to show impact with that. I mean, it really started out as like kind of a toy application for helpfulness with like CTF type stuff, but then the fact that it gets pulled in by these bigger, more serious projects, I'm sure they'll patch it at some point. All right, and that's all we have time for. So thank you guys, and this is AI, but an outtake blooper.